Imagine harvesting tomatoes, peppers, and salad greens in January in a Minnesota climate where outdoor temperatures plunge below 0 Fahrenheit for weeks at a time. Imagine doing this without burning any heating fuel, without running any electric heaters, without paying any utility bills for the growing operation. That's the promise and documented reality of passive solar greenhouses designed around principles that traditional Chinese, Nordic, and contemporary permaculture practitioners have refined across centuries of development. The approach uses intelligent design rather than energy inputs to maintain growing conditions through harsh winters, achieving year-round food production in climates where conventional greenhouses would require substantial heating to function. The design principles appear deceptively simple when explained, but their integration into buildings that actually deliver reliable winter growing requires careful attention to orientation, thermal mass, insulation, glazing selection, and ventilation strategies. Understanding how passive solar greenhouses work, what their construction requires, and where the approach fits. Contemporary food production helps explain why a small but growing community of practitioners considers this technology transformational for local food systems across northern climates. The fundamental physics of passive solar greenhouses exploit the substantial solar energy that reaches Earth's surface even during winter months at temperate latitudes. A south-facing glazed wall captures solar radiation across daylight hours, heating thermal mass structures inside the greenhouse that store energy for overnight use. Heavy insulation on the north, east, and west walls prevents heat loss that would otherwise undermine the system. Insulated night shutters or thermal curtains over the glazing during nighttime hours minimize heat loss through the glazing when solar input stops. The combination of solar gain, thermal storage, and heat loss prevention maintains greenhouse temperatures well above outdoor conditions across diverse weather patterns, enabling plant growth through seasons when conventional greenhouses would freeze without supplemental heating. The thermal mass configurations that successful passive solar greenhouses incorporate determine whether installations perform adequately across challenging winter periods. Water-filled containers provide excellent thermal mass through water's high specific heat capacity, storing substantial energy in manageable volumes. Masonry walls, concrete floors, and stone features provide effective thermal mass while contributing to structural integrity. Rock beds beneath or behind growing areas add mass while providing rooting environments for some plants. The total thermal mass in effective designs typically provides 3 to 5 gallons of water equivalent per square foot of south glazing, delivering storage capacity adequate to carry greenhouses through multi-day periods of limited solar input. The Chinese solar greenhouse tradition called Riguangwenxi has developed over 40 years to achieve remarkable winter growing performance across northern China's severe climates. These greenhouses feature thick earthen walls on north, east, and west sides, providing both insulation and thermal mass. Single-layer glazing on the south side, typically covered with insulated blankets at night, captures solar gain during daylight hours. Simple ventilation openings manage excess heat during warm periods. The resulting structures grow diverse vegetables year-round in climates where outdoor temperatures plunge below 0 Fahrenheit for extended periods without any supplemental heating. Over 800,000 acres of such greenhouses operate across China, producing substantial portions of the nation's winter vegetable supply through this passive solar approach. Dr. Wu Zhenhua, a Chinese agricultural scientist who has studied solar greenhouse development across 4 decades, has documented how the Chinese approach evolved through iterative refinement of design principles rather than sudden innovation. His research tracks how earlier versions from the 1970s and 1980s lacked adequate thermal mass or insulation to perform reliably through severe winter conditions, With progressive design improvements producing the effective contemporary designs, the evolution demonstrates how practical technology often emerges through extended iteration rather than single breakthrough moments, with attention to real-world performance-driving refinements that theoretical analysis alone might not identify. The historical development of passive solar greenhouse concepts in Western contexts traces through scattered experiments rather than the continuous development that Chinese greenhouse programs achieved. Scandinavian growers have used attached solar greenhouses for centuries to extend growing seasons. American experiments during 1970s energy concerns produced various designs with mixed success. Contemporary permaculture practitioners have refined approaches by combining Western design elements with insights from Chinese experience. The contemporary designs integrate lessons from multiple traditions into effective structures that perform reliably across diverse climates. Agatha Nordberg Johansson, a Swedish permaculture designer who has constructed passive solar greenhouses across Scandinavia for over 20 years, has documented how her designs perform reliably through dark Nordic winters when conventional greenhouses would be uneconomic to operate. Her designs emphasize thorough insulation of all non-glazed surfaces, substantial thermal mass calibrated to specific latitude conditions, and night insulation systems that prevent heat loss during long winter nights. The Scandinavian adaptations demonstrate how passive solar greenhouse principles translate to northern latitudes, where solar gains are limited and heat loss challenges are substantial. Her greenhouses grow productive vegetables through winters when outdoor temperatures drop to -20 degrees Celsius without any heating inputs. The growing capacity of well-designed passive solar greenhouses produces substantial food quantities that justify the investment and effort required for construction. A typical 200 to 400 square foot passive solar greenhouse can supply substantial fresh vegetables for a family of 4 across the entire growing season, including winter months when conventional local supplies don't exist. The productive capacity extends across crops suited to cool conditions, including leafy greens, root vegetables, alliums, cole crops, and some warm season crops through the warmer parts of the year. The food production value across 20 to 30-year greenhouse lifespans represents substantial economic return, alongside the food security and quality benefits. Now, for the obstacles and limitations affecting passive solar greenhouse applications. First, the design complexity exceeds what generic greenhouse plans typically address. Successful passive solar greenhouses require careful calibration to specific latitudes, climates, and site conditions that generic designs cannot accommodate. Glazing angles optimized for winter sun capture, thermal mass quantities matched to climate conditions, and insulation levels appropriate to regional temperature extremes all require site-specific analysis. The design investment deters builders seeking simple plug-and-play greenhouse solutions who expect to purchase a kit and assemble it without fundamental engineering. Second, the construction costs exceed conventional greenhouse costs substantially. Passive solar greenhouses typically cost $30 to $80 per square foot for proper construction, incorporating adequate thermal mass and insulation, compared to $10 to $25 per square foot for conventional greenhouses. The cost premium reflects the substantial thermal mass material and thorough insulation that effective performance requires. The higher initial investment deters some potential adopters, despite the dramatic operational savings that eliminate heating costs. Third, the space requirements include not just greenhouse footprint, but also adequate southern exposure without winter shading from buildings or trees. Urban and suburban lots may lack appropriate solar access despite having adequate land area. Property selection must consider solar access explicitly rather than relying on generic siting criteria. The solar access requirement constrains where passive solar greenhouses can be constructed, excluding some properties that might otherwise accommodate conventional greenhouses. Fourth, the skill requirements for successful construction exceed what typical DIY builders possess. Masonry construction for thermal mass walls, precise glazing installation for weather tightness, proper insulation installation, and integrated ventilation design all require building skills beyond basic carpentry. Contractors experienced with passive solar construction are rare outside specific regions, producing practical construction challenges for many interested property owners who might face difficulty finding qualified builders. Fifth, the management attention required for passive solar greenhouse operation exceeds what conventional greenhouses demand. Temperature monitoring, shutter operation, ventilation management, and plant care all require regular attention during varied weather conditions. Absences during extreme weather events could produce crop damage that active management would prevent. The management requirements affect whether the approach fits specific lifestyles and schedules. Despite these considerations, passive solar greenhouses represent a remarkable combination of food production capability, energy efficiency, and resilience that deserves serious consideration for appropriate situations. The food security advantages of passive solar greenhouse ownership become particularly apparent during supply disruptions that interrupt conventional food distribution. The 2020 pandemic, various weather events affecting California produced supplies, and periodic transportation disruptions have all demonstrated vulnerabilities in contemporary food systems. Passive solar greenhouse owners maintain fresh vegetable production regardless of these disruptions, providing meaningful food security beyond the nutritional and culinary benefits of fresh winter produce. The resilience considerations matter increasingly to households attentive to supply chain vulnerabilities. The nutritional advantages of fresh greenhouse-grown produce across winter months exceed what conventional winter food supplies typically provide. Vegetables harvested within hours of consumption retain maximum nutritional value, vitamin content, and flavor that storage and transportation inevitably diminish in conventional supplies. The quality difference produces real health benefits across the winter months when most households rely on produce that has traveled thousands of miles across extended storage periods. The health considerations add another dimension to the value calculation beyond pure economics. Reginald Kofi Boateng, a community food systems researcher who has studied urban agriculture initiatives, has documented how passive solar greenhouse adoption in community gardens and school programs produces educational benefits alongside food production. His research shows that students and community members engaged with passive solar greenhouse operations develop understanding of food systems, seasonal growing, and sustainability principles that extend beyond just the vegetables produced. The educational value multiplies the benefits from individual installations, particularly when greenhouses serve as demonstration and teaching platforms in community contexts. The cultural significance of year-round growing capacity in northern climates connects with traditional agricultural values, despite the greenhouse technology being contemporary. Traditional northern agriculture emphasized food preservation through root cellars, fermentation, drying, and other storage approaches that enabled year-round eating from seasonal harvests. Passive solar greenhouses extend this self-reliance tradition by producing fresh food year-round, rather than relying only on stored food through winter. The cultural alignment supports adoption among households connecting with traditional agricultural values while addressing contemporary sustainability concerns. The integration of passive solar greenhouses with larger permaculture systems produces synergies beyond pure food production. Greenhouses can incorporate livestock spaces for chickens or rabbits that contribute heat, fertility, and carbon dioxide beneficial to plant growth. Rainwater harvesting systems provide irrigation water while storing heat through thermal mass. Composting systems generate heat while processing organic matter. Aquaponics systems combine fish production with plant growth in integrated systems. The permaculture integration multiplies outputs from single structures while reducing overall system complexity compared to separate specialized systems. Delphine Moreau-Dubois, a French permaculture designer who has integrated passive solar greenhouses into diverse permaculture installations across Europe, has documented how integrated systems perform significantly better than component approaches. Her designs demonstrate that treating greenhouses as components of integrated food systems rather than isolated structures produces superior outcomes on multiple measures. The integrated approach requires more design sophistication, but rewards investment with substantially better performance across productivity, resource efficiency, and resilience dimensions that separate systems cannot achieve. The climate change implications of passive solar greenhouse technology include contributions to reduced food transportation emissions, reduced agricultural energy consumption, and increased local food system resilience. Each greenhouse displacing imported winter produce reduces transportation emissions meaningfully. The widespread adoption of such greenhouses across northern climates could shift portions of winter food production from conventional energy-intensive approaches to zero-carbon local production. The climate benefits scale with adoption rates, providing meaningful contributions to climate solutions when aggregated across the substantial populations in northern climate zones where the technology applies. The contemporary commercial products serving passive solar greenhouse markets provide accessible options for builders preferring purchase solutions over full custom construction. Kit greenhouses with proper proportions, insulation packages, and glazing systems can be assembled with moderate construction skills. Plan sets for various climate zones enable informed DIY construction. Consulting services provide site-specific design assistance. The product diversity supports adoption across various preferences and capabilities rather than requiring full custom design for all applications. Hamidou Diallo Sow, an agricultural engineer working on food security projects across sub-Saharan Africa, has studied how passive solar greenhouse principles might adapt to tropical highland contexts where cool season growing faces challenges from nighttime temperatures at elevation. His work examines how modified designs incorporating thermal mass for nighttime warmth and ventilation for daytime cooling could extend growing seasons. In highland regions where elevation produces challenging temperature patterns, the tropical adaptations demonstrate how passive solar principles translate across diverse climate contexts beyond just the cold climate applications where the approach originated. The glazing selection considerations for passive solar greenhouses involve trade-offs among light transmission, insulation value, durability, and cost that affect overall performance substantially. Single-layer polyethylene film provides excellent light transmission at low costs, but poor insulation and short lifespan of 4 to 6 years. Double-layer inflated polyethylene improves insulation meaningfully while maintaining good light transmission and moderate costs. Twin-wall polycarbonate panels offer durable construction with reasonable insulation, lasting 15 to 20 years before replacement. Glass glazings provide excellent durability and clarity, but at substantially higher costs and weight that affect framing requirements. The glazing selection affects both performance and economics substantially across greenhouse lifespans, with the optimal choice depending on specific priorities and budgets of individual builders. Contemporary passive solar greenhouse builders typically favor twin-wall polycarbonate for most applications based on favorable balance across all considerations. Hideko Matsumoto Ito, a Japanese greenhouse research engineer who has tested diverse glazing configurations across 20 years, has documented how combined glazing systems using different materials on different greenhouse surfaces can optimize performance beyond what uniform glazing approaches achieve. Her test installations demonstrate that using high transmission glazing on south surfaces while using more insulating glazing on east and west surfaces produces better overall performance than uniform treatment. The optimization requires more design sophistication but delivers meaningful performance improvements for growers willing to invest in refined approaches. The research methodology contributes to evidence-based design guidance that helps builders make informed material selection decisions. The irrigation and water management in passive solar greenhouses requires attention to the distinctive conditions that year-round growing creates. Winter humidity management prevents fungal disease pressures that the combination of plant transpiration and limited ventilation can create. Summer cooling through ventilation and evaporative approaches keeps growing conditions within plant-friendly ranges during hot periods. Water storage capacity for irrigation during extended dry periods supports reliable operation without dependence on external water supplies. The water management complexity exceeds what conventional outdoor gardening involves, requiring either automated systems or attentive manual management for reliable performance across seasons. The crop selection strategies that maximize passive solar greenhouse productivity across seasons involve careful sequencing of appropriate species to match conditions during each growing phase. Cool season crops including kale, spinach, chard, lettuces, arugula, cilantro, carrots, beets, and alliums grow productively across winter months when solar gains are modest and temperatures are cool. Warm season crops including tomatoes, peppers, eggplants, and cucumbers extend through longer seasons than outdoor growing permits. Succession planting approaches maintain continuous production by sequencing crops with overlapping maturity dates. The crop planting sophistication distinguishes productive greenhouses from marginal ones, with experienced growers producing 3 to 5 times more food per square foot than casual operators through careful attention to appropriate species selection and planting timing. Beatriz Alencar Silva, a Brazilian tropical agroforestry specialist who has collaborated with Nordic passive solar greenhouse builders on extension season growing in temperate contexts, has documented how companion planting and polyculture approaches adapted from tropical agriculture improve greenhouse productivity substantially compared to conventional monoculture planting. Her demonstration projects show that diverse plantings mimicking natural ecosystems produce higher total yields with reduced pest pressures and improved nutritional diversity compared to traditional row cropping approaches. The diversity principles apply across climates, even though specific species selections differ. The cross-pollination of tropical and temperate growing practices demonstrates how diverse knowledge sources contribute to contemporary sustainable agriculture development. The pest and disease management in passive solar greenhouses requires integrated approaches since the enclosed environment can concentrate problems that outdoor growing disperses. Biological controls including beneficial insects, predatory mites, and microbial products address pest pressures without chemical inputs. Cultural practices including crop rotation, sanitation, and diverse plantings reduce disease pressures proactively. Physical barriers and exclusion approaches prevent pest establishment when possible. The integrated management approach delivers reliable production while avoiding the chemical input dependence that conventional intensive agriculture requires. The skill development required for effective integrated management adds to the overall learning curve, but rewards development with sustainable productive operations across extended timeframes. The economic analysis of passive solar greenhouse investments requires considering both direct food production value and broader benefits that conventional analysis often overlooks. Direct food production value for typical installations ranges from $800 to $2,500 annually in market value equivalents, depending on crop selection and management intensity. The higher quality of fresh, homegrown produce compared to commercial alternatives adds value, difficult to quantify but meaningful to consumers accustomed to supermarket quality. The recreational and educational value for family members engaged with greenhouse operation adds further dimensions. The resilience value during supply disruptions produces benefits that may not be monetary, but matter substantially during challenging periods. When comprehensive value assessment considers all dimensions, well-managed passive solar greenhouses typically achieve payback within 8 to 15 years, while continuing to provide benefits across 25 to 40-year structural lifespans. The attached greenhouse configuration integrating directly with a home produces particularly attractive benefits by combining greenhouse heat contribution to the attached structure with living space, access to greenhouse environments. Excess heat, generated during sunny winter days, can transfer into adjacent living spaces, providing supplemental heating while maintaining greenhouse operation. The shared thermal envelope reduces overall heating costs for both spaces. Direct access from kitchen or living areas makes harvest and care more convenient, encouraging the regular attention that productive greenhouses require. The integration advantages have attracted substantial interest from homebuilders seeking comprehensive sustainability approaches, though construction complications around shared walls and moisture management require attention to ensure lasting integration success. Consider what passive solar greenhouses mean for households interested in food production, food security, or reduced environmental impact. The year-round fresh food production capability transforms household food systems in ways that seasonal conventional greenhouses cannot match. The elimination of heating costs while producing substantial food creates economic returns that accumulate over decades of greenhouse operation. The food security benefits during supply disruptions matter increasingly in uncertain times. The nutritional advantages of fresh local produce during winter months improve health measurably. The educational value for families and communities builds understanding of food systems and sustainability. The integration with broader permaculture systems multiplies benefits beyond pure food production. The cultural connection with traditional agricultural values honors heritage while serving contemporary needs. The question isn't whether passive solar greenhouses deserve serious consideration for appropriate situations. The question is, why local food movements haven't embraced this proven technology more enthusiastically, despite its demonstrated performance in Chinese commercial applications and permaculture installations across diverse climates. The answers involve construction complexity and skill access rather than fundamental limitations of the approach. For households with adequate solar access and construction resources committed to local food production, passive solar greenhouses offer remarkable capabilities that conventional approaches cannot match.